Okay, right. So here we started, or to say we were dealing with eigen operators, eigen functions, and all those things in the last previous class. And in the previous class, we tried to go for the Schrodinger's wave equation. Okay. Can you tell me what is Schrodinger's equation in a very simple form or in the simplest way? Word slow.
So total energy is equal to kinetic
Beautiful.
energy plus
That's it.
potential.
Okay, Ma. Very good. Very good. Thank you, Ma. Thank you very much. Okay. So remember that way. Okay. Schrodinger equation, if at all, if you use the word and think, okay, it is something which I don't know, then it will be very difficult for you to grasp it. But if at all, if you come back and try to understand what is it, it is nothing but a total energy equation. Okay. Now, before going to that, let us see. So in quantum mechanics, every time a quantum mechanical particle is represented by a wave function, and that wave function will be a plane wave equation. Okay. So from that plane wave equation, if at all, if you want to determine the position, or if you want to determine the momentum, or if you want to determine the velocity, or kinetic energy, or angular velocity, whatever may be it, if you want to determine the physical quantities or physical observables, then for every physical observable, there should be a corresponding eigen operator. So when you apply this eigen operator on the wave function, that gives you an eigenvalue which is equivalent to the physical observable, which is equivalent to the physical observable's value. Okay, so that's the point that we should remember here. Okay, the wave function is represented by psi of x comma t, that is position and time dependent. X comma t undachu, y comma t undachu, or it may be r comma t. R implies general direction. Okay, x and x direction, y direction, z direction. Okay, it could be arbitrary direction or along x y z, any of the directions. A is the amplitude of the wave, and e to the power of I kx minus omega t is the variation in the value of psi, that is wave function. Okay, that's actually the variation part of it. Okay. Now, when I take a e to the power of I kx minus omega t, that implies it's a wave traveling along x direction, positive x direction. Okay. What about negative x direction expression? 5 seconds. 5, 4, 3, 2, 1. Okay, what will be
Minus
the...
x in place of x.
Minus k.
That's it. So some of you remember that. That's good, Amma. Very good. Okay. Okay. All of you can answer that question. Okay. Right. So that is a minus x replaced with x. That will give you the plane wave equation traveling along negative x direction. Okay. Now, because x is x is dependent upon psi is dependent upon x comma t. X is position. So if you want to know the momentum of the quantum mechanical system or quantum mechanical particle, then what you have to do it, you have to differentiate psi with respect to x. Sir, if I differentiate psi with respect to x, how will I get momentum, sir? Remember what I said yesterday. Okay, position and momentum are state variables. Okay, because position and momentum are state variable set or state variable pair. Okay, if you differentiate psi with respect to one of the state variables, then you will get the value of the other state variable. Okay, not exactly, but in terms of that. Okay, so when you differentiate psi with respect to x, you will get momentum, and when you differentiate psi with respect to t, you will get energy of the wave function. Okay, so that's how you should remember. Okay, blind ga gurtu pettukoni manam differentiate chestunnamu edo vastundi. If at all, if you are going in that direction, after some days you may forget. But if at all, if you remember this way, that implies if you understand it this way, then you may not forget it at all. So I take psi and differentiate it with respect to x. So what I get is ik psi. Okay. So this is a eigen operation. But the problem is eigenvalue is an imaginary value. Imaginary values do not represent anything physical. So what I do is I multiply both sides with minus I. When I multiply it with minus I, the operator will be minus I d by dx of psi. This operation actually gives me k psi. So what is k? Propagation vector. So if I ask you, okay, what is the operator for, if I ask you what is the operator for angular velocity, okay, omega. If I ask you what is the operator for angular velocity, what will it be? I did not tell you, I know. Okay, I know that I did not tell you about that. Okay, but if I ask you what will be the eigen operator for angular velocity, okay, what will be your answer? I'll give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3,
Do by dt.
2, 1. Yama?
I do by dt.
బ్యూటిఫుల్ దట్స్ ఇట్ ఓకే ఇక్కడ కే కావాలంటే ఐ ఓకే మైనస్ ఐ డూ బై డూ ఎక్స్ అనుకున్నాము ఓకే వెన్ వీ వాంట్ ఇట్ ఫర్ okay we already have seen that okay size this expression and dou by dou t gives you minus I omega, right? So when you have this expression then what do you do? Multiply this with I. So I d by dt will give you omega psi. I d by dt of psi gives you omega psi. So if somebody asks you, okay, I have a wave function and you have to determine the angular velocity of the wave function, then what do you have to do? You just have to, okay, apply the operator I d by dt on the wave function and whatever eigenvalue you get, that will give you the angular velocity. That will give you the angular velocity. Okay, I think okay, you're following. Okay, I know that okay, I did not tell you how to find the angular velocity operator, but this is not something which is what do you say, okay, very big thing. Okay, it's a simple thing that you can see and say, right? Okay. And the others who okay who still feel that there is something which you did not understand, you are free to ask me any question anytime. Okay, so minus I h cap dou by dou x is the momentum operator, and similarly I h cap dou by dou t is the okay I dou by dou t is the omega operator, and I h cap dou by dou t is the Hamiltonian operator or the total energy operator. So I make use of these two things. I make use of these two things and I can determine the potential energy operator. Potential energy operator is nothing but I h cap dou by dou t minus okay I h cap by 2m minus okay 1 by 2m minus I h cap dou by dou x whole square. Okay, that is nothing but your p square. Okay, 1 by 2m p square operator. That is total energy minus kinetic energy.
Sir, you are on mute, sir.
Okay,
Sir,
right.
you're not audible.
Yeah, okay. I don't know how, but I went on to mute. Okay, okay, sorry. Coming back. So if I want the potential energy is nothing but total energy minus kinetic energy. Total energy operator is given by this expression and kinetic energy is given by this expression. So total energy operator minus the kinetic energy operator gives you the potential energy operator. Okay, that's what I asked yesterday, and okay, you people have answered me. That implies okay, you're very good. Okay, so now going for the Schrodinger's wave equation. Schrodinger's wave equation is nothing but total energy is equal to kinetic energy plus potential energy. Okay, now I put it in operator form. When I put it in operator form, h of psi is equal to p square by 2m plus v of psi. Okay, what is p? The momentum operator. Okay, what is h? Total energy operator, the Hamiltonian. Okay, so this is the Schrodinger's wave equation in the operator form. Now what will I do? Okay, for h I'll substitute I h cap dou by dou t, and for p I'll substitute minus I h cap dou by dou x. Okay, and combinedly this will become the Schrodinger's wave equation in differential form. Okay, so this is the Schrodinger wave equation in operator form. This is the Schrodinger's wave equation in okay magnitude form. That is total energy is equal to kinetic energy plus potential energy, and this is the okay Schrodinger's wave equation in the differential form. Okay, now here what do we have is psi. Psi is dependent upon position as well as time. Here our psi okay was a variable or a function of position and time. And the operator I h cap dou by dou t, that is total energy operator, is also a function of time. That means it is dependent upon time. So whatever expression you see over here has time concept, or to say time aspect into it. Because we have time aspect in it, we call it as Schrodinger's time dependent wave equation in differential form. So I added two more words, that is time dependent, okay, into this name. Okay, basically I really did not do anything great. Okay, I just added two words, that is to say it is time dependent. Okay, this equation is again total energy is equal to kinetic energy plus potential